Hey everybody, welcome back to another round of physics, and yeah, let's get going. As promised, I said that I would do a couple of example problems dealing with the RC circuits. And so I thought, okay, well, first off, what happens if we put not one branch, but two branches in parallel? And you could probably get a sense of what you would expect to happen, but it's always nice to go through and kind of show that that's the case. So let's go ahead. First off, we pretend that the switch closes at time equals 0, and we want to know the behavior of this entire circuit as the capacitors C1 and C2 become energized. Okay? So let's go ahead and we'll pick a different color here. Let's go ahead and first off, we have some currents that we should put in. So we have the current running through the battery. I'll call that I naught. And then you have currents going through each of these branches. I'll call that I2 and I1 respectively. Okay. Now, next up, of course, let's go ahead and label our high and low potential sides based off of either the battery or alternatively based off of the direction that we have chosen for the current flow. So there we go there. Okay. And next up, of course, we can also think about our junctions. We have a junction here, which I'll label A and B. And finally, we're at a situation where we can now apply our Kirchhoff's laws. Okay. Keeping in mind that from our drawing, we have three unknowns, namely the currents running in each of those branches. Okay. Well, let's go ahead. KCL would say, I'll go ahead and look at junction A, right? So remembering that because we only have two junctions, if we use one, we won't be able to use the other one. And so I can write I naught, the current coming from the battery, is equal to I1 plus I2, which seems pretty boring. Now let's go ahead and apply KVL for the other two equations. And what I'll do is I will consider just the left loop, and then I'll consider the outside loop. So I'll think of the left, and I'll think of the outside. And for the left loop, as I walk around, I get a jump of the battery is equal to the drop across the first capacitor, so what I'll call Q1 and C1, plus the drop across the first resistor. And similarly for the outside loop, yeah, you can see it's Q2 over C2 plus I2 R2. And since we're dealing with the energized capacitors, the capacitors that are being charged, we know the relationship between Q1 and I1, or similarly Q2 and I2, namely that the charge that gets deposited on the capacitor is related to the current flowing through the resistor, namely by a derivative. So we can take advantage of this idea here, Q2, and we'll see where those will come in handy in a brief moment. Now what we are left with is trying to solve this system of equations. And again, on the surface, it looks like we have 5 unknowns, when in reality we only have 3, right? Because the charges on the capacitors are related to the currents flowing through the resistors. So now we need to finagle our way around in order to solve these equations. Now, one of the interesting things is that technically this equation is no longer linear. Because I am taking derivatives, that means that I no longer have it linear in currents. I have some other GAC going on. And so how I'm going to solve this equation might look a little bit different than usual. First off, I notice that right here, let's start with the equation that comes from the left. And the first thing that I am going to do is I am going to go ahead and take a derivative of that. Now again, you don't necessarily have to do that. You could, for example, substitute in this relationship between I and Q. you could substitute it in right here, and you could find yourself sitting on a first order differential equation that we'd have to go through and use integration techniques to solve, like the characteristic equation. I'm going to go the other way. Let me go ahead and take a derivative of this. And because this is a constant, we get a 0 equals 1 over c1 Now, of course, I will now substitute in the fact that the current is given by dq dt. And so I end up with something that says 1 over c1, the current 1, plus the derivative of the current equals 0. And you can see why I took the derivative. Knowing that that's a constant, I can take a derivative to make it equal to 0, and that sometimes makes the equation easier to solve. Well, let's go ahead and separate. And we see very quickly that we end up with the same equation that we know and love. So I'll move that to the other side. I get a negative I1 over RC. Or if I prefer, I get the derivative I1 over I1 equals negative dt over R1C1. And you know from doing all of our integration stuff from the charging capacitor, that means that I1 as a function of time is equal to some constant e to the negative t over R1C1. Good. And now you notice, hey, wait a minute, if I compare the equation that I got from the left-hand side as compared to the outside loop, mathematically, these two equations look the same, which means the solution that I found for the first, let me go ahead and box it, I can verbatim rinse, wash, and repeat. In other words, I have an I2 of t, which is some constant. Now, it's a different constant, doesn't necessarily have to be the same, but otherwise it has the exact same form as that first equation, R2C2. And boom, there are the two equations which determine the current through those respective branches. Okay. Now again, we know that A and B, they must be some combination of probably the battery potential divided by a resistance somewhere. And we can get at that. We could say, for example, that for the brief instant when the switch is closed, C1, capacitor 1, should act like a wire. Right? At time equals 0, the uncharged capacitor C1 and the uncharged capacitor C2, these should both act like wires. In other words, for a brief instant, the circuit that I deal with can be modeled like this, where the capacitors are completely absent. Well, if I asked you for the current running through R1, you would say, okay, well, the current running through I1 at time equals 0 should just be V battery over R. And similarly for I2, should be V battery over R2. Well, that tells me what my values of A and B should be. Right? At time equals 0, the exponential becomes 1, and that A must make sure to match this value. And so at the end of the day, you get what you would probably, or as I hinted at, should anticipate. The idea that each of those branches charges up as like a separate capacitor in parallel. Okay. And finally, of course, because of Kirchhoff's current law, you know that, hey, the current coming from the battery has to be the sum of those two. Now, I can't simplify it anymore. Well, I guess I could pull out the common factor of V, but at the end of the day, there's not much additional simplification going on here. Okay. So this ensures that charge is conserved. So there we go. There is everything that we need to know about the entire circuit. Pretty cool, huh? I guess I could make comments like, for example, you can see that because of the values of R2 and R1 and C2 and C1, these two capacitors don't necessarily have to charge at the same time, right? R1 and C1 gives you one time constant. There's a second time constant for the second branch, and those don't necessarily have to be the same. And you can see this is going to be the combination of the two exponentials. Not much further insight to give you there. Yeah, it's just nice to see that Kirchhoff's laws hold and still work even with more than one capacitor and resistor. Well, why don't I give you another example? This one has some interesting applications, both in terms of heat transfer, has some interesting applications in terms of transmission lines, interesting applications in terms of cell dendrites, or maybe it's axons. So what I have here, let me walk you through it. Again, I have a battery. Maybe I should put a switch in here. Maybe I should have done that. Let's say we have a switch and that we're going to close. And now you notice that I have an RC circuit, but the capacitor and the resistor are no longer in series, but they're in parallel. So a slightly different idea. Of course, you can see the capacitor is in series with that resistor in the sense that if I go through the capacitor, I must also go through the resistor. Okay. So you have this situation. Now notice here, I have put in a voltmeter. So a V with a circle in it is a voltmeter. So there is no current traveling down this branch because voltmeters by design have a very high resistance. In fact, for purposes of this analysis, we'll assume that the resistance is infinite, so that zero current travels down that branch. Now, more than often than not, you won't see the voltmeter drawn in. I think part of that is because we don't want to accidentally say that there's some current. And so what a lot of textbooks will end up doing is rather than drawing the voltmeter in, they will simply leave two open terminals, and it is understood that you're measuring the potential drop across those two locations in the circuit. Okay. So I would like to hook up my voltmeter right there and measure what the output is between that side and that side. Okay. So the question is, what is V out in terms of RI, RM, C, and V in? Okay. Go ahead, pause the video if you have a minute, if you want to take a stab at it. Okay, let's go at it. So first off, of course, I should follow my own advice. So I will go ahead and call this I0. And we have I1, I guess I'll call it IC, running through the capacitor, and I'll call this one IR, running through the resistor. Okay. Next up, of course, let's label the high and low sides. So we've got high and the high side, the low side, the low side. And of course down here, let's not forget this lowly resistor in the bottom. Next up, let's go ahead and label some junctions. So I have junction A. And of course you could think that tiny wire in the middle, that's a perfect wire, so you could imagine shrinking that whole thing down into a single junction. So maybe that's not even the best. Oh, excuse me, I got overzealous there. Maybe for conceptual purposes, perhaps I should label that junction down here instead, just for conceptualization. So we'll call that junction A. We'll call this junction B, as in Bravo. Okay. And now we're off and running like a bale of turtles. We have three unknowns again. And so we must come up with a system of three equations. Well, first off, we have I0 is equal to IC plus IR. And that's as far as I can take it, simply because that's, one junction that I can use. So there you go. So let's go ahead and choose a couple loops. I'll choose the one with the battery capacitor, and then I'll choose the one with the battery resistor. Okay. Rock and roll. So starting at the battery, we get a battery as the jump, and then I go across the capacitor, which serves as a drop. And then, of course, I go through this bottom resistor. So I got I naught Ri. Similarly, for the battery resistor loop, I get IR Rm plus I naught Ri. And now we have our three equations, our system of equations that we'll need to sit down and solve. Now again, I'm going to assume that my capacitor is uncharged. And so there is a relationship between the charge on the capacitor and the current running through the capacitor. Now what am I going to do here? Let's do the same thing. I'm going to solve this bottom equation. I'm going to solve this bottom equation for IC, this middle equation. Hi, my name's Greg. I will solve the bottom equation for IR, and then once I have those solved, I'm going to substitute them in back up here to get a value for I naught. Okay. I think that'll do it for us. So let's go ahead. So thinking about the battery capacitor for a second, I'm going to go ahead, and my first inclination is simply to take a derivative to get rid of that Q in the VBAT. So taking a derivative, I get 0 equals the current running through the capacitor plus, now here we have to be careful because I'm taking a derivative of the current coming from the battery. It always seems weird, right? The change of the current coming from the battery is somehow related to the current going through the capacitor. I don't know why, that just always seems a little weird, different to me. Well, let's go ahead. If I solve for IC here, so I move that to the other side, I get negative R di naught dt equals IC over C. Or I get that the change in the current coming from the battery times RC is equal to the current going through the capacitor. So we'll need that. Very good. Well, second off, let's go after this sucker. Of course, that sucker, you can see that I can rearrange it straight away in order to get the value of the current running through the resistor. In fact, why don't we just go ahead and do that down here? We get something that says the current running through the resistor is equal to the potential of the battery minus the potential drop across that bottom resistor, what I called Ri, all divided by Rm. Right? And double check me that I haven't done anything sneaky there, or I haven't dropped a negative sign, which I'm so well known for. Okay. And we're going to take those two expressions now, and we will substitute it right into here. Right. So I have taken the Kirchhoff's current law, I have substituted in the currents that I have, and now what we need to do is we need to rearrange this equation so that we can solve it. So first off, I'll go ahead, let me get the I naught all onto the same side. So I have an I naught, actually let me multiply through by Rm first, just to get rid of the fraction. All right, well, if I get that over onto the other side, what I get is I naught times the two resistors added together. Okay. And this should look, sort of familiar, right? The two resistors are sort of in series, right? Like, well, I shouldn't say sort of. Resistor Ri is in series with Rm. right? If you go through the resistor in the middle of the circuit, Rm, you are forced to go through the resistor at the bottom of the circuit, Ri. And so this first term here is kind of encompassing the fact that those two resistors are in series. Now we look over here, you've seen, for example, Ri and a capacitance multiplied together. That's somewhat reminiscent of a time constant that requires a charging of the capacitor. Now we'll see a little bit more where that pops in, but I just thought, okay, you can sort of see where some of these elements come from. Let's go ahead. Let's do our usual song and dance. I'm going to take a derivative here just because I want to avoid the characteristic equation for purposes of our mathematics. So we have Ri plus Rm. Those are just constants. And what we're going to do, let's see here. We can solve this differential equation for the term di naught dt. In fact, if you want to relabel it, you could relabel that as some new variable. We'll call it x. And so this equation can be rewritten as x plus Ri Rm c dx dt equals 0. Right? Sometimes that helps. Sometimes it's a little harder to see it when you have these derivatives in here. But if I just simply replace one of the derivatives with some new variable, it makes it a little easier to see. Well, let's go ahead. Let's rearrange this so that we get the x's on one side and then everything else on the other. And what we get, I'll go ahead and do this in 2 steps just so that it's not too fast. So I'm going to take the resistors, move them over here in the time, and I'll put the x on the other side. And I'll go ahead and flip to another page here. So take a screenshot if you need it. You say, but wait, Greg, I already know how to solve that. We integrate out, right? We put in the integration constant. We raise everything to take e raised to the power of everything. And what we end up with here is that we end up with this rigmarole. Some integration constant, a, times the exponent, which is negative Ri plus Rm, all divided by Ri Rm c, and that whole quantity is multiplied by the variable t. That is equal to x, which of course x was equal to our change in current di naught dt. So you can start seeing how now we don't have just a simple, RC time constant. This whole thing in here is the time constant, and you notice that it varies according to both of the resistors and the capacitor. So whatever's in there, that's the 1 over tau. Right? And that should give us a little bit of comfort that, if we check it, we have an ohm divided by an ohm squared times a farad, which is equal to a 1 over ohm farad, which is, of course, equal to 1 over seconds. Okay. So, good. Always good to double check. So everything looks like it's kosher there. But we're not done, right? We're not done yet because we don't want how I naught is changing. We want actually the value of I naught. So we do a second integration, and we get that the current coming from the battery as a function of time is this constant A, and boom, there we go. We now have the current that is coming from the battery. Yes, it's ugly. Remembering that we're dealing with a charging capacitor, and I keep insisting on forgetting to put the switch in. Okay. We are dealing with the charging capacitor. This means that at time equals 0, we can think of the capacitor as being a perfect wire. Right? An uncharged capacitor, for a brief instant, acts like a perfect wire. And so rather than this circuit, we essentially are dealing with this circuit. Right? The capacitor acts like a wire, 0 resistance, so all of the current should go through the capacitor. And we have, for a brief moment, this circuit. In other words, I naught at time equals 0 should just simply be equal to v over Ri. Right? Yeah, good, good, good. How about for a long time? Yeah, for a long time, so as t goes to infinity, the capacitor now equals, looks like a break in the circuit. And so no current flows through that branch. And so you can remodel that like it going through Rm, and then of course it still has to go through Ri to come back. So you have Rm and Ri. And so at long times, I'll put it like this, but of course you know that I mean the limit as time goes to infinity. You should end up with some sort of thing like this, where the current is Rm plus Ri. And we can use those two ideas to figure out what the values, the coefficient integration values are, A and B. Now, there's no easy way around it. I'll call this condition 1, I'll call this condition 2. There's no easy way around it. We just have to go through and do it. So, excuse me. So what do I have here? Let's start. I will go ahead and write out the equation. Of course. So let's go ahead and use those two conditions. So first, at time equals 0, we said that the current running through the circuit has to be V over Ri. Okay. And so we'll take this equation, and so I of 0 must be equal to, well, we have this huge GAC thing out in front, right? I mean, I got to admit that I wish that I didn't have to write this all out. I could give it some new variable, but it's always good to at least see it once. We have e to the 0, right? Time is 0 plus b. Okay. And so we can see that this will give us a relationship between a and b. You can see I can just add this to the other side, and so I get something that says b is equal to v over Ri plus a times this rigmarole quantity. I guess I could have given this some new variable name. Physicists love to do that just because we're lazy and don't want to have to keep writing stuff out. Okay. So there is b in terms of a. So now I have to go to the other condition that we had. And the other condition is, as time goes to infinity, the current approaches V over Ri plus Rm. In other words, the capacitor starts acting like a brake. And so what we get is V over Ri plus Rm, right? That's the current as a function of time. Now you can imagine if I plug in a large value for t, that first term goes away, right? It disappears, goes to 0. This term goes to 0, which means the first term in this expression is 0, and I get just b is left over. Okay, well, now we have an expression for b. We should be able to go through and plug it in here. So maybe I didn't need that dividing line at all, and figure out what a has to be. So plugging that in, we have v over Ri plus Rm minus v over Ri is equal to a times rigmarole. Of course, we want to get a common denominator, and so you could have Vri minus v times the quantity Ri plus Rm. So we get a goody-goody moment right there, all over Ri times Ri plus Rm. Quantity. So don't forget those parentheses. Of course, we have a couple of goody-goody moments. The first is, you notice that we have a Vri minus a Vri, and so we get some cancellation. We get that this term and that term cancel. Furthermore, you notice we have an Ri plus Rm. on both sides of the equal sign. So we can get rid of those. Okay. So let me just take a gander here. Okay. So let me go ahead. I'll switch over to a new page. Notice that we'll have negative, oh, excuse me, wrong color. Notice we'll have negative VRM divided by RI is equal to A RI RM times C. Maybe? Yeah. Oh, goody, goody. Notice the RMs cancel as well. RM cancels the RM. And what I'm left with is that A is equal to negative V over RI squared times C. So I naught of T, which was equal to negative A, so we have negative V over RI squared C. So we have plus B, V over RI plus RM. Okay. Cool, huh? Yeah, I guess you have a little bit of goody-goody, right? One of these RIs cancels this R right there, so I'll take care of that. Okay. And yes, you could as you, oh wait, we have a C cancels the C, right? That C cancels the C. Okay. And so we could do a little bit more simplification. You could say something like this positive and positive. So you have a term V over RI plus RM. And it's always good to do this just because you notice this thing out front, that's in terms of amps. So everything that I put inside this, square bracket should be unitless. So let's see, what do we get? We get RM over RI, right? E to the negative T RI plus RM, all divided by RI RM C, okay, plus 1. There we go. And of course, you can see that R divided by R is unitless. And so everything looks good there. Yeah? Okay. Now we're finally to the point. Right, now we're finally to the point where we can say, okay, well, V out, which was equal to the battery minus I naught times R I. Yes. But notice this RI here, right? Well, no, I can't say that. Excuse me. I was going to say it cancels out, but it doesn't. So I got to be careful there. So we have this RI. So we can take this whole expression and then paste it in, right there. You can imagine I'm taking that whole sucker and I'm going to multiply by RI. So I just distributed the RI inside the square bracket. And then you can see that this term, VRI over RI plus RM, will cancel with this term, VRI RI over RM. So you can imagine that term, let me do this in some other color so you can visually see it, that term cancels that term. And lastly, well, what do we have at the end of the day? I'll go ahead and write this out for you. So at the end of the day, what we end up with is that the potential measured across the resistor is given by this expression. Notice we have the 1 minus, kind of interesting, but we have that. What does that look like? That looks like, if I plot this as a function of time, this term in the square brackets will essentially look something like this, where it rises up asymptotically to some value. Of course, you can see what the value is. It's this coefficient out in front. Okay. And so that's what happens as the switch is closed. which is kind of interesting, right? That's just a different behavior. Now, where is this really interesting? So is this interesting? A lot of people will use this for a transmission model, a signal transition model. And it's not by accident that I use the subscripts Ri and Rm. Okay? So we stopped here. We called this Ri, we called this Rm, and C. Okay? And we stopped here and we said, hey, what is the output at these two terminals? But you could imagine drawing in another circuit that looks exactly the same. In other words, and I'll do this one, let me do it in blue just so that it pops a little bit better. Okay. You could imagine drawing in a second one of these with the same value Rm, with the same value of C, and the same value for the internal Ri. Okay. And then you could keep going, right? So you could imagine stringing these all together. Okay. Now, for the red one, you can say, hey, wait a minute, V out is given by this expression. Okay. Now, for the blue one, right, V becomes, so what was V, the input potential here? The input potential for the blue circuit is the output potential from the red circuit. And so if I want to know the output for the blue circuit, I'll label it I'll do it in colors. It's the output from the red circuit times all of this rigmarole, right? So I got to do it again. Rm over Ri plus Rm times this sucker, 1 minus e to the negative t times Ri plus Rm over yada, 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 right? But V out we could substitute in here, right? And so we see that for that second circuit, the blue one, the output is going to be the battery times this ratio Rm, Ri plus Rm squared times this quantity in the parentheses squared. That's for the second one. Of course, you could imagine for the third one, this is V out, you know, if I plugged in a third one down the line, so you already know what to do. Rinse, wash, and repeat. So instead of a squared, you'd end up with a third here. You'd end up with a third here, et cetera, et cetera, et cetera. Pretty cool, huh? Yeah. Now, what's interesting about that? Imagine, okay, because of these extra resistors that I've labeled Ri, okay, the overall resistance for, you know, like imagine when I throw the switch, some of the current will come all the way down to this orange piece, right? But if I compare the amount of current that, say, flows through this resistor here in the orange piece as compared to the amount of current that flows through the red resistor, right here. Okay. Well, this orange one will have all of this stuff raised to the third power, okay? Whereas the red one, it's all raised to the first power. In other words, the current flowing through the red circuit, part of the circuit, is going to be much larger than the current running through the yellow part of the circuit. Now, what happens though? The capacitor fills up, and what will then happen is that more current will start going through the blue circuit, right? As the capacitor fills up, more and more current gets diverted this way, and we'll start filling up the blue circuit. Okay? And then after the blue capacitor gets filled up, then the orange capacitor gets filled up, and then, you know, yada, yada, yada down the line. Okay? This is, for example, how a dendrite can be modeled in a brain cell, right? Like, I can't remember if it's a dendrite or an axon. Maybe it's the axon part of a dendrite, right? What happens is that there is a signal, the switch gets closed, and the part of the dendrite close to the cell body. And then the question is, how does the signal propagate down the long axon to the end of the dendrite to signal to another cell in the brain? Okay. Well, now we have an idea. right? The switch is closed. That's the start of the signal being sent from the neuron. And then you get a potential, or you could think of current traveling down here, or you could think of it as a difference in potential between those two electrodes. Okay? But you eventually get this sequence, this cascade of signals going down the line until you reach the very end. So that's why it's sometimes referred to as the transmission. I think it's called the transmission model. And this is a very simple one. Okay. Oh, yes, and also in terms of terminology. It's not by accident. RM, I was thinking this as the resistance of the membrane. So the membrane resistance, the sheath of the axon that makes up, the cell membrane. And RI is just supposed to be R internal, the internal resistance of the cell. Okay. So there you go, just in case you're interested. Of course, you could change that. It doesn't have to be RI and RM. Some other transmission line problem as well. Well, I think that's probably enough. Just 2 examples and some interesting applications. So I'll leave it there for right now. Of course, you have your homework and you can start working on that. And yeah, we'll keep moving. So, hey, I thank you for your attention. Keep up the good work. I'll see you next time.